Hello, Science Lines. Hello, I am Lara, as you probably know. This is lesson 2 of IGCSE, Waves. You don't actually need to have seen lesson 1. I'll do a very brief recap, and then this whole lesson is just going to be loads of me talking at you, basically, amazing facts that I've just learned, and giving you a few questions as well. Right, first of all, last week, do you remember? We were looking at slinkies, we were looking at the 2 different kinds of waves, right? So I was pinging a slinky from side to side, the coils were vibrating from side to side, and the energy was also being passed from side to side. I'm making myself feel a bit sick, but you get it, right? The vibrations were moving from side to side, and the energy was also being passed along the slinky from side to side, and that was called a longitudinal wave, yes? So sound waves travel like that. Air particles or whatever, sort of booshing into each other like that at your ear. And then we looked at another kind of wave where the energy is still travelling, for example, from side to side, but the vibrations are then up and down, like that. What was that wave called? A transverse wave. Very good. And we looked at how ocean waves on the ocean are transverse waves. Both those waves, sound waves, boosh, 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 and ocean waves, are what we call mechanical waves. A slinky is also a mechanical wave. A mechanical wave is a wave that needs particles to travel. So today, we're looking at waves that do not require particles to travel. So sound doesn't travel through space, right? There's no particles. There's no booshing can happen. These waves, they can move through space. A lot of lessons, including mine in the past, have just like launched into how you use these different waves. I'm going to very briefly try and kind of give you a little picture of what they actually are. A lot of the times it doesn't get said because it's very complicated. We will do a lot about electromagnetism in a future lesson, but if you've got a couple of magnets with you, some of you have done this before with me, just get the magnets, move them towards each other. What do you experience? I mean, you know, don't you? You can feel them pulling towards each other or pushing away from each other. But how do the magnets know that each other is there? Do you know what I mean? Like, you don't have to make them touching before you feel that force. I'll do it on the table, in case you don't have magnets. Look at this. Right, so I push this magnet very, very slowly over to the other magnet, and it doesn't get that close before, yeah, that happens. So what's going on there? Is it like last week? Is it air particles sort of booshing into each other and carrying the message to one magnet that the other magnet is there? No, it's not. No. What is happening is that magnets have around them something called a magnetic field. More of this like much later on. Magnets have a magnetic field around them. So when you put magnets together, they sort of experience each other's magnetic fields, and that's what they feel. Right, time for a very, very short PowerPoint with speech bubbles. Yeah, you love it. To just kind of briefly introduce these incredible waves we're looking at today. In 1819, In 1819, Danish scientist Hans Christian Ørsted was giving a lecture involving magnets and electricity. In the middle of the lecture, he happened, I'm thinking about it, just put a compass down next to a wire that had an electric current flowing through it, and was very surprised by what happens next. You ready for a famous theory of science special effect here? What? The compass started moving. It did, which was very surprising at the time. So, charged particles, like electrons, if you've done an electricity module with me, you know about them. Charged particles are surrounded by electric fields, just like magnets are surrounded by magnetic fields. Inside an electric wire, as many of you know, charged particles are moving. And it turns out moving electric fields generate magnetic fields, which was messing with the compass. This was a very cool thing to discover in front of a massive audience full of people. I don't know how he handled it. Q, incredibly famous and amazing Scottish scientist and legend, James Clerk Maxwell, who just used maths. He wasn't like a practical scientist particularly. He didn't do loads of experiments. He just used maths and thought, maybe space is full of electric and magnetic fields that vibrate as waves and travel at, does complicated James Clerk Maxwell maths, 300 million meters per second. And this is the kind of diagram that he came up with, right? Magnetic fields and electric fields vibrating and moving through space at right angles to each other. And that is what we're learning about today. Incredible. Someone was gently pointing out on my Facebook lesson the other day, I say amazing a lot during this lesson. So this is the electromagnetic spectrum, all the different kinds of electromagnetic waves that travel using these electromagnetic fields. And they're everywhere, right? Because charged particles are moving everywhere. So electromagnetic waves are traveling all through space, they're passing through our bodies right now. The only reason that we think of light as being special is because light just happens to be the wavelength of electromagnetic wave that our bodies have evolved to detect, right? So you'll see that the only difference between all these different electromagnetic waves vibrating through space is their wavelength, okay? So radio waves have a very long wavelength, some of them are like miles long. Gamma waves have very, very short wavelengths, and then all the others, X-rays, ultraviolet light, infrared, microwaves, they're all in the middle. It just so happens that our eyes have evolved to be able to detect electromagnetic waves that are in this sort of band here that have this particular wavelength. So we call it light. Quite often you kind of call all these waves light, and you just say that that bit is visible light, so it's the light we can see. So one important thing that you have to remember for your IGCSEs is that other than their wavelengths being different, or their frequencies being different, right, the amount of waves per second, they're all the same. They can all travel through space, they don't need particles because they're using these force fields. They all travel at the speed of light. They all travel at, oh, it's YouTube, I can write forwards. They all travel at, could write forwards if I had a pen that worked, 300 million meters per second. You remember that maths lesson we did ages ago? You remember how if you start here and you count back the zeros, you can write this in a nicer way. So that's where my decimal point is at the moment. If I move this decimal point back 1, 2, 3, 4, 5, 6, 7, 8, I can put it there and write that as 3 times 10 to the power 8 meters per second. Is that all right? So 3 times 10 to the power 8 meters per second means 3 and 8 zeros meters per second. It's fast. I mean, most of you will know light is the fastest thing in the universe, okay? Yeah, I think that's it. Yeah, that's it. I'm going to give you 4 questions. 2 of them you should know the answer to because I literally just told you, and 2 of them I want you to just do some sort of good guessing. So you might know a little bit about these electromagnetic waves already. Just tell me what you think. Question 1, which of these waves, radio, microwave, infrared, light, ultraviolet, X-ray and gamma, travel at the speed of light? Question 2, which of them can travel through space? Question 3, which of these waves do you give off? I should have said humans, like it's not personal to you. And 4, which 3 do you reckon are most damaging to human cells? So I think 2 of those you're going to know, and 2 of them you're going to have to give me a good guess. Questions 3 and 4, obviously it's more than one. In fact, both of them, it's 3 actually. Oh, excuse me, so snotty. I'm so sorry. Ugh. What do you reckon? I'm hoping that you've got 1 and 2. Which of these electromagnetic waves travel at the speed of light? All of them. They're all the same. Apart from their wavelengths, right? So the longest wavelengths, I'll tell you that in a sec. Which of the above waves can travel through space? Yes, all of them. You're getting it. They're all the same apart from their wavelength. Which of these waves do you give off? What a brilliant question. If I say so myself, let's think about that. If you have got a candle with you and you are allowed to light candles on your own, or if there's an adult with you, I don't want to be patronising, but it's hard to do physics and think about physics and watch telly and deal with fire at the same time. It's not advisable. But if you've got an adult in the room or they said it's okay, just light a candle, or if not, you can just watch mine. Which electromagnetic wave has appeared on the screen? We've got a new electromagnetic wave. I mean, obviously it was around anyway. What have I done? Well, by lighting a candle, we've introduced some more light into our lives, haven't we? Why is this candle now giving off light? And it wasn't before. I mean, yeah, it's on fire, obviously. There's a lot of obvious answers to that question. I'll tell you. Well, I should say, the longer the wavelength, the less energy the wave carries, okay? So radio waves carry the least energy, and gamma waves carry the most energy. What's happened is that the candle has got hotter, and the hotter an object is, the more energy its electromagnetic waves carry. Okay, so everything gives off electromagnetic waves. Everything. You, me, ice, everything in the whole universe gives off electromagnetic waves. But this candle is now giving off light because it's got hotter. And like I say, the hotter something is, the shorter the wavelength of its electromagnetic wave. So this candle is now about 1,000 degrees C. So it's hot enough to give off light, which is your clue for what, I wish I hadn't even blown that out now. Yeah. Which is your clue for what waves you're giving off, right? We are not hot enough to give off light, obviously, but we are hot enough to give off infrared. Did you know that? Some of you will know this already, because humans might only be able to detect light with their bodies, but we have invented all kinds of different amazing machines that can detect all these different wavelengths, which is what makes them so incredibly useful. So you might have seen an image like this before on a thermal imaging camera. So this camera is not detecting light, it's detecting infrared radiation, infrared waves. So the dark bits are cooler, and the bright bits, like the tyres, I guess because they're on the road, got a lot of friction, and the lights, they are the hottest bits, okay? So everything that has a temperature, so everything, gives off infrared radiation. I did know that. What I didn't know is that it's a spectrum, right? Humans actually also give off a little bit of microwaves and a little bit of radio waves. I know. So if you were going to draw a graph, I hope there's no physicists watching. I don't think this is particularly accurate. But if you're going to kind of draw a graph to show the waves that we gave off, we'd be giving off mainly infrared. But we would be giving off a tiny little bit of microwave and radio wave as well. Because the important thing is to remember, humans have labelled these waves, right? Nature hasn't put a line between radio waves and microwaves. It's just that humans have said, oh, once the wavelength gets kind of this short, we'll call it a microwave. Whereas the candle, right, is giving off a lot of light. So maybe the graph of the candle would sort of look something like that. I don't know. You get what I mean though. It's now giving off light as well as infrared. It's got hotter, so the electromagnetic waves it's giving off have kind of shifted up a bit. Right. And we also use infrared radiation for cooking stuff, don't we? Electric grills. Again, because it just infrared just happens to be the right temperature to cook things, right? That's what we want to use it for. So a lot of people think that infrared radiation is like the hot radiation. That is not true. All of these things generate heat or are given off by hot things, but you wouldn't want to cook something in like loads of light waves because it'd be too hot. If something was so hot that it was giving off light, it would be like 1,000 degrees, it would burn your food. So it just so happens that on planet Earth, we generally, like, sort of our nice warm bodies are just the right temperature to give off infrared. The grills that we cook our food with, they're just the right temperature to give off infrared. It's like a coincidence. Okay, which of them are most damaging? I think you might have got that. So just to run you through this, because there's an awful lot to learn about this on your spec. This is all the uses of electromagnetic waves that you need to mention on your specification. The ones in italics are Cambridge only. Cambridge really needs you to learn a lot of stuff. And I've put all this in a sheet for you in my Facebook group. But yeah, hopefully that has gone some way to explain why we use heaters and night vision equipment with infrared radiation. The ones that are most damaging. Did you get that it's just the last three? Because they've got the most energy, right? So have you got some sun cream with you? It's not quite the right weather for it yet, but I said to bring something if you had it that protects you from the sun. Have a look at your sun creams and see which electromagnetic wave you can see mentioned, all right? Have a look. Which electromagnetic wave is mentioned on your sunscreen? You might be able to do this without even having it in front of you. So gamma rays, incredibly dangerous, carry an awful lot of energy, very damaging. X-rays, very, very damaging. Ultraviolet light, also damaging. When I say damaging, the posh word, which you need to know for your GCSEs, is ionizing. You remember ions? So atoms have got protons in them with electrons kind of whizzing around the outside, if you like. And usually they've got the same amount of electrons and protons, but if one of the, say, electrons gets knocked off, the atom gets charged, yeah? Because now it's got sort of slightly more positivity than it has negativity, and you call that an ion. You remember. So gamma rays, X-rays, and ultraviolet waves are all what we call ionizing, because they can basically pull atoms apart. They've got so much energy that if they hit an atom in your body, they can ionize that atom, and is incredibly damaging to cells. So these are the ones that can cause cancer. Gamma rays, incredibly dangerous. X-rays, obviously humans deal with them, but in small doses. So someone who works with X-rays will have like a lead apron on and will stay away from the X-rays, because if you get constantly bombarded with X-rays, that could be very dangerous. And if you've been looking at your sunscreen, you will find they've probably got something to do with UV written on them. This one says UVA, UVB, and UVA's in a circle. This one just says UVA. So they protect you from ultraviolet rays. My question to you is, all electromagnetic waves are travelling through space towards Earth. All of them. Look, you can see it here in this diagram. So why does sunscreen only protect you from ultraviolet and not X-rays and gamma? What's that about? I have just told you that gamma waves and X-rays and ultraviolet rays, as well as the others, are all travelling through space towards Earth right now. They're all incredibly damaging. In fact, gamma and X-ray are the most damaging to skin. Why does your sunscreen only protect you from ultraviolet radiation? I'm very pleased with this question. And when I asked it in my Facebook lessons that I have comments on, everyone was giving me loads and loads and loads of good suggestions, and hardly anyone got it right, which is always, as a teacher, a kind of good thing to see. It means you're thinking, but I also get to teach you stuff. Have you got an answer in your head? Let's have a look. Here's a massive clue for you. I'm going to give you 10 seconds to think about it. Can you rank these waves from 1 to 7, where 1 can travel really easily through Earth's atmosphere and 7 can't travel at all through Earth's atmosphere? What do you reckon? Radio, microwave, infrared, light, UV, X-ray and gamma. Which one do you think can travel really easily through Earth's atmosphere, and which one can't travel at all through its atmosphere? And you rank the ones in between. Well, 5 seconds now. How we go? It may or may not sort of be a trick question. Oh, I'm so sorry. Oh my goodness. Right, the answer is 1 can travel easily. That would be radio, and it just goes 1, 2, 3, 4, 5, 6, 7. Yeah. The answer is gamma rays and X-rays. They can't travel through Earth's atmosphere. They get blocked. Hooray! They get absorbed, I should say. And I've put lucky, question mark, exclamation mark. No, it's not lucky, is it? It's not lucky. If we lived on a planet that was being constantly bombarded by gamma rays and X-rays, humans would not have evolved. Maybe something else would have evolved. I don't know. But yeah, gamma rays and X-rays both get absorbed by Earth's atmosphere. Be careful, they don't like bounce off. They sort of soak in, if you like. They get absorbed by the atmosphere around Earth, mainly ozone. Some people were saying that on Facebook, which was very impressive. So ultraviolet, there are a few different types of ultraviolet. You don't need to know this for your IGCSE. I just think it's interesting. There's UVA, which has sort of quite a long wavelength. There's UVB, that's got a shorter wavelength, and there's UVC that has a really, really short wavelength, right? Because there's like an infinite amount of wavelengths in each of these things that we're calling electromagnetic waves, okay? So UVC waves, ultraviolet C, are kind of up here near gamma, so they can't get through Earth's atmosphere either. Hooray! So we don't need protecting against UVC because the atmosphere is doing it for us. UVB are sort of in the middle. Hardly any of them get through either. We don't really have to worry about UVB. But UVA has quite a long wavelength. It's got a long enough wavelength that it can get through Earth's atmosphere, but it's got a short enough wavelength that it's going to ionize people's cells. So UVA is the one that we've got to watch out for, and it's the one that sunscreen is protecting us from. How good is that? And then once you get to an even longer wavelength, you get to light, which can obviously get through Earth's atmosphere, but is not ionizing. It won't damage your cells. Right. So this is good news for us, because gamma and X-rays get blocked, but it also means that radio waves and microwaves travel really easily through Earth's atmosphere, which is super useful for various reasons, which you need to know, and also it's just interesting to know. Radio telescopes are a thing. Did you know that? What? Have you heard of radio telescopes? They're massive, because radio waves are massive. So if you want to study something in space that gives off radio waves, which astronomers do, then you've got to build a really, really big detector, because the radio waves that you're detecting might be sort of 20 meters, their wavelength might be 20 meters long. But yeah, they get through Earth's atmosphere easy. So you can just put your telescope on the ground and just like sip your tea on the surface of Earth while you're observing radio waves. Nice. Another use for radio waves is, radios, innit? Because again, they've got to travel easily through Earth's atmosphere, right? And radio waves do. Okay, moving on to mobile phones, because this is weird. Microwaves get used for mobile phones and also to cook food. This is the thing that gets people very, very confused about electromagnetic waves. Let's talk about that bit. I actually had to look up, why aren't radio waves used for mobile phones? Because they both travel easily through the atmosphere. So the reason, there's a few different reasons why we use microwaves and not radio waves for mobile phones. Because they both do it fine, they both travel through Earth's atmosphere. But one of the reasons is that the bigger the wave that you're emitting and detecting, the bigger your detector has to be. And we don't want our phones to be massive. So microwaves are smaller, so our phones can be smaller. I didn't know that. It's only one of the reasons, but it's such a nice sort of simple thing to remember. So microwaves, you will notice, right, there's a lot of people get confused and think because microwaves heat up our food, that they might also be cooking our brains. And there's a lot of misinformation on the internet about how like microwaves cause cancer because they go near your head and they also cook food. These are the ones that are ionizing. The gamma and the X-rays and the ultraviolet have got enough energy to pull atoms apart. These ones don't have enough energy. The reason that microwaves cook food is just it's really, really intense microwaves. Any of these waves, if you get them really, really intense, they will have a heating effect. And yeah, if you do talk on a mobile phone for a long time, you do notice yourself getting quite warm. That's because you've had a lot of microwaves near your head. They are heating you up, just like that would happen with infrared and with light. So yeah, hopefully that has gone some way to explaining why. Oh, yeah, so the reason that we use sorry, that's a lot of talking from me this lesson, but I just love it all. The reason we use microwaves to cook food, one of the reasons is, again, how far they can get into things. Microwaves can penetrate to the centre of food. If I wanted to cook, say, if I wanted to heat up my coffee, I couldn't use light waves, could I? Because light waves are clearly hitting the cup and bouncing back into my eye. That's how I can see the cup. I couldn't use radio waves because radios wouldn't even see the cup. They'd just travel straight through the cup. But microwaves are just the perfect wavelength to get inside the cup and heat up the food. And they also get absorbed by water. So that's why we use microwaves for cooking, as opposed to any of the other things. Okay, moving on. Oh yeah! Oh! I need my TV remote control to show you this next bit, and my husband ran off with it fairly reasonably last night. You could go and get your TV remote control as well. If you've got time and no one's using it, I will be 2 seconds. Here we are. Right, if you've got a TV remote control that's got a little light bulb in the front, there's a really good activity you can do to investigate a use of infrared waves. So your TV remote control possibly communicates with your TV using infrared. So if I look at this remote control with my eyes, what am I seeing if I press the buttons? I'm seeing nothing, because my eyes have not evolved to detect infrared. I cannot see infrared with my eyes. But your mobile phone camera, if you've got one, it's obviously been built to detect light. That's the whole point of it. It's a camera, light goes in. But it's a bit like loosey-goosey on either side, yeah? It's not perfectly only detecting light. It can also detect infrared, or sort of at least quite short wavelengths of infrared. So if I hold this up to my phone camera, you should see something, because the camera is going to convert the infrared into light, okay? I know, so excited, right? I'll have to come round here where it's a bit darker. Yeah, here we go. Not that dark, is it? Let's see if you see anything. You ready? Yeah, look at that! Come on, am I the only one that thinks that's cool? That's ace. So this is an infrared signal being given off. We can't see infrared, but yeah, my camera is converting it into light, purple light. We will look at colour next week in the all ages lesson, which you should also come to. So there you go. You can have a go at that, can't you, at home after this. Right, so that's one of the uses of infrared. Again, I didn't know why we used infrared for TV remote controls and not microwaves or radio waves. And when I looked it up, it turns out it's dead simple, really. It's just that it's much cheaper to build something that emits and receives infrared. So the expensive ones, like microwave and radio waves, we use for posh things like phones. And TV remotes, yeah, you just want them to be cheap. So they emit infrared. I know. Finally, right, we're getting there. So we've been through loads of uses. We'll briefly look at X-rays, because they are very damaging, but they're also incredibly useful for looking inside bodies, right? Again, you couldn't get an image of your bones using radio waves, they just pass straight through your hand. You couldn't get an image of your bones using light, because they would just bounce off your hand. But X-rays travel through skin and tissue, but are absorbed by bone. So you get this lovely image. Not this is just a picture. But this kind of thing, yeah? So that's what we use X-rays for. I think you probably knew that. And finally, the slightly confusing use of gamma rays is that they can be used to treat cancer. So gamma rays damage cells and can cause cancer, but if a person actually has cancer, like has a tumour, some cancerous cells, a good way to kill those cancerous cells is to direct gamma rays at them, and they will kill those cells. But you want that to happen. You see what I mean? So it's a bit weird. Gamma rays cause cancer and are also used to treat cancer. Okay, it's finally time for you to do something else. A sheet of recaps, because that was a lot of information. I totally just information dumped you there, sorry. Can you please match the wave to the use? Oh, I didn't even mention which one sterilises water. It's one that hasn't got a use yet, to see if you can work it out. So, grilling food. Which wave do we use for grilling food? Which wave do we use for mobile phones? Which wave do we use for thermal imaging? Which wave do we use for sterilising water? Which wave has not had a use yet, so I had to cram that in there. Which wave is used for treating cancer? Which is used for cooking, because it penetrates deep into food and is absorbed by water? Which wave travels through skin but is absorbed by bone? And which two of the waves are used for communication, because they travel most easily, not perfectly, but they travel most easily through Earth's atmosphere. And if you do that, I've got some puzzles for you that I'm very proud of. I just found this information out, basically, this week. So it's supposed to be hard, it's supposed to challenge you. Because you have got all the information, I think, that you need. What wave would you detect if you wanted to use a satellite to get images of clouds around the Earth at night? What wave would you detect if you wanted to map the ice on Earth's oceans? I've told you that ice gives off far less infrared than water. And what detector would you use if you wanted to study bursts of the highest energy waves in space? Which wave would you be wanting to detect? And where would you put the detector? Right, I'm going to count to 40 in my head. Oh, actually, I just got... Oh, no, it's all right. I'm on 35, if that helps. excuse me. Okay, how have you got on? These ones are hard, but I think if you do process of elimination, you might be able to work a couple of them out, or have an educated guess. Okay, here's the answers to the first one. So well done if you said that radio and microwaves are both used for communications because they travel the most easily through Earth's atmosphere. Microwaves are the ones that can get to satellites most easily. So microwaves are used for like satellite TV and things. Microwaves are used for mobile phones. Microwaves are used for cooking food. They're dead useful, aren't they, microwaves? Infrared is used for thermal imaging and grilling food. It's ultraviolet that is used for sterilising water. X-rays are used because they travel through skin and absorbed by bone, and gamma rays are used to treat cancer. Well done if you've got all those. Right, so we're hovering above space in a satellite. We're looking down on Earth, and it's night time, and we want to get pictures of the clouds. What on earth are we going to do? If you got those answers, I'll pull you back up. Well, let's do this by process of elimination, okay? We've got our detector on our satellite. We're looking down on Earth with the clouds. Gamma and X-rays, some people were saying on Facebook, but they get absorbed by clouds. So they're going to travel down, get absorbed by the clouds. They're not going to bounce back into our detector. So that's no good. That won't give us an image of the detector. Same with ultraviolet light, right? That's largely going to sort of pass through or be absorbed. So the answer was infrared. That is what they use to look at clouds at night. Oh yeah, and obviously there is no light because it's nighttime. So yeah, if you want to take a picture of a cloud in the daytime, you can use the light. But yeah, infrared's the best thing to use at night. And also, infrared tells you the temperature of the different bits of the cloud, which obviously light doesn't do. But if you use an infrared detector, you can see, oh, that's a colder bit of the cloud, that's a brighter, warmer bit of the cloud. So yeah, it really helps you to see more detail, according to NASA. Right, the next one. This is my favourite. I didn't know this. I was thinking about the fact that everything gives off infrared. And I thought, well, I wonder if really, really cold things give off microwaves. So I looked it up. And yeah, they do. I found this very cool bit of the NASA website explaining how they take pictures of sea ice using satellites. So I'll show you. Sure they won't mind. They're ever so good about sharing information, aren't they? Here we go. So they've got an aqua satellite. How does it see sea ice? Microwaves. Everything on Earth's surface, including people, emits microwave radiation. Properties vary, blah, blah, blah. Ice emits more microwave radiation than water, yeah? Because it's colder. So the ocean with ice on it appears much brighter than the water. Yeah? You get that? G'day. And there's a picture that they've taken, or an image that they've taken using microwaves. So water is warm. Well, it's warmer, right, than ice. So water is giving off mainly infrared, but ice is giving off far more microwaves. So yeah, if you use a microwave detector, then the water looks sort of quite dark because it's not giving off many microwaves, and the ice looks nice and bright. I'm just delighted by this fact. I didn't know that. And finally, if you were looking to detect the highest energy waves in the universe, then you would be trying to detect gamma waves, wouldn't you? Well done if you said that. Where would you put the detector? There's like gamma ray bursts happening in the universe, and you want to observe them. You got your gamma ray detector. You're sitting on Earth. Is that a good idea? No, that's not going to work, is it? One, because if any gamma rays went into your detector, they'd also be hitting you, and that would be bad. But also because gamma rays, as we know, are absorbed by Earth's atmosphere, so that you'd have to put it outside Earth's atmosphere, right? And that is indeed what scientists have done. So NASA have got gamma ray detectors on satellites so that they can detect them. Right. Whew. That is the end of the lesson. There's an awful lot of information in there. So on your usual homework sheet that I've put in my Facebook group, I've suggested that you spend your week basically looking through the big long list that I've put on the sheet of all the different uses that you need to know of all these waves and the dangers of some of them, and just research them, maybe put a PowerPoint presentation together for yourself or make a poster, something that's going to help it go in and also help you with your revision later. Because I had to ask, I've learned loads just because some things I didn't quite get, like why is infrared not used for communications? Or yeah, like I say, do cold things give off microwaves? I've learned loads. I'm very happy with myself this week. So I think you should do that too. And I've put some of the links in that I used to help you you can find your own as well. I thought the last thing we would do is, last week I showed you the cartoon of Wormy and I said, can you pick out which waves are in the cartoon? So I thought, well, I'll show you the cartoon again and see if you can tell me let's see if you can spot any new ones or if you've got a better understanding of them now. I'll just do it quickly. Theatre of Science presents Wormy, Theatre of Science mascot Wormy, in Trouble at Sea, images by vectc.com. Lots of different waves appear in the story, make a note of those you see. If you've got your sheet from last week, maybe you can check against that and see if you've learned anything else this lesson. I love living on a boat, says Wormy. Nice calm sea today. Just ripples. Okay, IGCSEers. Can you name how many, or name as many mechanical waves as you can see in this picture? How many mechanical waves are there, I should say, in the picture? And how many electromagnetic waves are in the picture? How many mechanical waves? How many electromagnetic waves? Do you remember what a mechanical wave is? I'll give you 10 seconds. If you don't know what I'm talking about, you can just list all the waves again. What's a mechanical wave? And which mechanical waves are in this picture? There are two. There must be at least two mechanical waves in this picture. And at least two electromagnetic waves as well. 5, 4, 3, 2, 1. So the mechanical waves, the waves that need particles, are the ocean waves. Obviously, if you took away the water particles, there would be no ocean waves. That's a mechanical wave. And the sound wave, right? Wormy speaking. So sound waves are mechanical waves. They have to have particles in order to exist. And the electromagnetic waves, I just got light, and then someone pointed out on Facebook, Wormy must be giving off electromagnetic radiation as well. She's giving off infrared. So light, infrared, ocean waves and sound waves. Well done, we got those. I'll just microwave some soup, says Wormy. Psst, says the radio. Breaking news, an earthquake has just happened. Oh no, says Wormy. She runs to her TV remote control. Which wave is coming out of her TV remote control? Luckily, only one person was injured. They are in hospital having x-rays, says the newsreader. Unfortunately, the earthquake triggered an enormous ocean wave. We saw last week how the newsreader is evil. Sorry about that. So, it's not terribly subtle, this, is it? Did you get that? What have we had? Microwaves, radio waves, and x-rays. Okay, let's proceed. I must get to the steering wheel of the boat, says Wormy. So she does. She runs off. She gets stuck on a treadmill. Oh, no. Right. Worm on a treadmill. With your new wave knowledge, what 2 words could you use to describe a worm on a treadmill? Come on, this is your last how much have you learned task. You've got a super long worm, she's on a treadmill, she's moving like this. What do you reckon? It's going to be annoying some people that I'm saying her. Wormy is just a her, that was just decided. I know that worms don't actually do that. What 2 words? Don't say like wacky wormy wave like people were doing on Facebook. What scientific ways of describing a wave could you describe a worm on a treadmill? There's 2 words. One of them is mechanical, because she's using, the wave is because of particles, right? If you took away the worm particles, the wave wouldn't exist. So it's a mechanical wave, and I would say transverse as well, yeah? Because the vibrations are at right angles to the oscillations. Well done if you got that. And is that it? I think that's it, isn't it? She goes to the window, she sees a lifeboat, she says she'd better wave. We learned last week that is not a wave. And this isn't a wave either. This is just a great pun. Help is on the waves, and that's the end. Whew. So hopefully that made a little bit more sense to you now. Yes, right, I'm going to go. That is the end. Next week, you can, and indeed you should, watch my all ages lesson as well as the IGCSE lesson. So some of you really like to come to both, but at the moment the IGCSE lesson and the all ages science lessons that I teach have been the same. But next week they split off a little bit. So they're both about waves, but I'm going to do about colour with the all ages people. And we're going to do something else. Can't remember what. Maybe reflection. So yes, if you don't usually come to both, then you should come to both. I'll put them both up on YouTube so that you can see when they are happening. If you want to support me, Obviously, you totally can. I mean, that needs to happen from some people. If you want to throw me £5 a month, £5 a month. That's all I need. Can't give me more if you like, but I'm getting £5 or more from enough people that this is literally my job. So if you sign up, I will send you nice things. I'll send you rainbow glasses. It's a very good time to get rainbow glasses, isn't it? Because we're just about to learn all about rainbows. I will send you a Theatre of Science magazine, which is excellent if I say so myself. I'll send you an explanation of how the rainbow glasses work. Again, actually very useful as well as fun. Oh, hello. Hello, Betty and A. Good to see you. I'm just on my Facebook page seeing if anyone's left me any hello messages. Because if you're watching live, then you can say hello. It always makes me feel good. But thank you very much everyone who has watched this live. I always say it makes a massive amount of difference. If there was no one watching live, I would just go away and have a cup of tea and I would never get around to teaching the lesson. So yes, thank you very much for supporting me. Thank you for liking this. I can see the likes and that is making me feel good. Thank you for subscribing and all that stuff. Yeah, I'll see you next week or on Thursday for the Lego Storytime show about earwax. Bye!